This talk, as you can see from my affiliations, I do sort of 3 different things, and this is the least profitable thing I'm doing. Data science and F-sharp consulting is the sort of more profitable, but philosophy of science is something that I really got sort of interested in as I was finishing my PhD, where I think a lot of people at that stage are like, oh, what am I actually doing here? And you can sort of just take it as a lament or go to your psychiatrist. But I sort of thought it's a really interesting problem how programming as a discipline or computer science as a discipline, how do we do what we do and why do we do it in certain ways? This talk is sort of using some of that reading, and I'll end with a useful list of references. I'll have movies you can watch and books you can read. So I'll warn you at the end so that you can take your phones and take a picture. But to start with, the talk really sort of started with a Twitter discussion, and I thought I'll better anonymize those. But there's a thread where someone was saying, ha ha ha, are pure functions invented or discovered? And one of the answers is, this is really interesting. I wonder if there's a paper about that. And I sort of came in and said, well, there's an entire academic discipline about that. But sadly, it lives in the humanities school, so we don't really know about it because it's like hidden in the other building. There's a discipline called philosophy of science, philosophy of mathematics, and this is one of the sort of basic questions they would think about. So what I want to start with is to just sort of give you a couple of pointers to some of the interesting ideas that people have thought about in this other strange building on the campus. It's not going to be complete at all. I'm just picking a couple of random things that I've read because my background is computer science. I'm not a philosopher. So even my knowledge is just sort of a couple of random books. That's still more than a paper. And the sort of basic thing that many people probably have heard about is Platonism. And this is the idea that goes back to Plato, that mathematics, or in the sort of modern incarnation, that mathematical objects are some sort of independent, eternal entities that exist outside of the world as we humans interact with it. So if you believe that when all the mankind dies and the universe explodes, there will still be number 5, then that's probably a Platonistic belief because you sort of believe that the mathematical entities have some sort of objective existence outside of the world. And this is sort of a perspective that quite a few people believe. I think a lot of people who don't really think about it will sort of think about something like this until they start thinking about it. And then you sort of discover all the potential problems. And one book that I'm going to refer to later on talks about this and says, this is fine, but there's a problem with this, and they call it the romance of mathematics. The problem is that it's a great story that really attracts lots of people to mathematics because you get to work with this perfect world, but it also is what intimidates people. It sort of helps to maintain an elite because you can say, well, either you see the eternal truth or you don't, and if you don't, that's probably, you just don't do it. And it sort of rewards the incomprehensibility partly as well. So the sort of Platonist view is something that makes the mathematics look like a perfect sort of universal truth, and that really disconnects it from people, which has nice aspects, but it also has sad aspects, meaning that it makes it really hard to learn or engage with it. So another interesting perspective is that a lot of science is really sort of social process. A lot of mathematics has really interesting social process behind this. There's a really, really lovely book by Imre Lakatos where he's saying something like mathematics doesn't grow through the increase of number of established theorems. So it's not just we sort of discover more and more of this ideal world, but it grows through improvement by speculation, criticism, and that's what he calls the method of proofs and refutations. So the idea is you sort of come up with some mathematical thing, and then the community refines it, someone criticizes it, you find a counterexample, you have to go back, update your definitions, and so on and so on. The book, he sort of goes through an example of a polyhedra. So there's the famous Euler formula for polyhedra, and once you sort of start digging through it and you say, well, what if the polyhedra actually has a tunnel through it? It breaks the formula, so then you have to do this sort of revising and so on. Just a wonderful quote from the book is by a mathematician, I forgot his first name, but his last name was Hermit, who's sort of well-known contributor to sort of differential calculus and so on, where at one point he writes a letter saying, I turn aside with a shudder of horror from this lamentable plague of functions which have no derivatives. And he does this because at that point the definition of function just didn't allow this. Like, this is a monster. This is something that just shouldn't exist, and maybe we should just drown the people who create these. And that's part of the process where later on the mathematical community says, well, we'll have to update our definitions to make this work, and it's the sort of social process that makes mathematics happen. The other interesting thing you can say about mathematics is that it really depends on some culture as well. And there's sort of more extreme takes on this idea that really mathematics, everything is just culturally determined. It's just a social construction. But fairly sort of reasonable take you can have is that you say, well, a lot of mathematical ideas are really have some cultural aspects in it. So culture-specific ideas often find the way to the very fabric of mathematics. And a couple of examples, and people always, computer scientists like pictures of Hilbert, so I put Hilbert here. But he's actually relevant because all these things here. So one of the sort of Western culture things we have is going back to ancient Greeks, and it's the idea that there is some sort of notion of essence. And in Greek, I was like, you build everything is from fire, or everything is from water. That's the essence. But this idea that things have essence really is something that's sort of part of the Western culture. The sort of Hilbert idea, or idea around the time, was that human reason is really a form of, or you can sort of treat it as a form of logic. And the other thing is that given a subject matter, we can look for foundations. That's something that's very, very Western. Why don't we look for roofs? No, we look for foundations. And so this is sort of a point that maybe if you didn't even have a Western culture, if sort of Chinese mathematics evolved independently from the Western mathematics, maybe even the Chinese wouldn't have Lambda Calculus, because they just don't need to look for essence and logic and foundations. And finally, so this is probably going to be the sort of biggest chunk of my talk, is And Alvaro, who was giving a talk yesterday, already mentioned this book by Lakoff and Nunez called Where Mathematics Comes From. And it's written by cognitive linguists and sort of cognitive scientists who are saying the only mathematics we can say anything about is the sort of brain and mind-based mathematics. So if there is some eternal mathematics, well then, might be, but you just have no way to work with it. The only thing you really have access to is what happens in the brain when you do mathematics. So let's use cognitive science to try to look at how people think when they do mathematics. In practice, this means if we want to find out anything about mathematics, how it's done, what it is, we should look at cognitive sciences and find the ideas there and see what they tell us about mathematics. So what I'm going to say now is just a few more, a bit more background on this cognitive science of mathematics, what we actually know, or what the cognitive scientists know about how brain does mathematics. And the one really, really important thing there is that cognitive science, there's sort of a lot of work in that area that shows that abstract concepts are understood in terms of more concrete things via metaphors. So metaphor isn't just something that poets use when they want to write a best-selling poem. It's something that we just use in our everyday thinking without even sort of consciously realizing it. I think this is really important. I think someone mentioned yesterday a recent debate about something like functors or other fancy category theory constructions. Even those things, there is a scientific evidence that when you're thinking about very abstract stuff, you're doing it in terms of concrete things. So I think this is a really, really important note that is worth keeping in mind, even when you're programming. Remember that abstract concepts are really understood in terms of concrete things. And the interesting part is that they sort of, a lot of mathematical ideas are a mathematization of some real-world stuff, some ordinary ideas. So, for example, derivatives are, you can sort of understand them, you learn to think about them in terms of changes of speed or immediate change. So derivatives are the sort of thing you do when you're in physics, when something changes speed, you sort of think about it in terms of derivatives, but also that's how derivatives actually are sort of explained. That's how people think about them. And how do we use all this to actually understand mathematics? There's a couple of things. So there's some basic mathematical concepts that you can actually find by doing experiments on babies. So there's some basic sort of built-in maths, and then from these you can sort of construct more complicated structures via metaphors. And there's conceptual metaphors which sort of explain basic things like numbers. And then you can get more complicated structures that are sort of more abstract by building metaphors on top of other metaphors. Does anyone have baby around 6 months, ideally? You can do this. So the trick here, the idea is, do we sort of, can we check whether babies have some built-in maths, like 1 + 1 = 2? And the experiment you can do is that you take these two Mickey Mouses, put them somewhere, and then hide them so that if you remove one, that's happening here, the baby can actually see that you're removing one of the two Mickey Mouses. And then you put down your blind, and either the expected thing happens, so there's just one Mickey Mouse because you removed the other one, and you'll see 1. Or you can, you need to have some sort of hedge in this, where as you remove 1, you'll sort of stick in 1. So even though you had 2, you removed 1, you're still left with 2. And the experiment is that you will sort of watch. Babies don't really tell you very much in 6 months, but you can watch how long they stare at this thing. And the sort of result is that when the unexpected things happen, they will be confused and they will stare at this for longer. I think you need a lot of babies to actually make any conclusions, but you can try it with 1. So that's the sort of built-in mathematics that babies have, and this works for like 1, 2, 3, and I think 4 is too much. But the way we construct sort of more abstract mathematical concepts like numbers is that we will link them to something that happens in the world. So in the world, even if you're 6 months old, you can recognize 2, 3 Mickey Mouses, and they're objects in some collection, and that's the metaphor here links this collection of objects to number system. So you will think about numbers as collections of objects. Then you'll say the size of the collection is the value of the number. Bigger collection means greater number. And you build this mapping between the concrete real-world stuff and the abstract mathematics. And the way we can find this is through linguistic examples. So the way we talk about numbers the way we talk about numbers very often uses the same words that you use for collections of things. So when you say add onions and carrots to the soup, this is addition. You're just putting stuff in a collection. Or if you say which is bigger, 5 or 7, well, no, I don't know. They're both 14 points on my screen. They're not bigger. So the bigger really sort of refers to this via this mathematical metaphor. And the equational properties of numbers, that's something that you can, again, get from the real-world stuff. So if you have two object collections, you put them together. Or if you have 3, right, if you have A and B, you have some object collections, you put one into the other or the other into the first one. There will be same number of objects. And that's commutativity in mathematics. The metaphors often have some sort of limitations. So if you have a collection, there really is no good way to talk about 0. You need other metaphors like movement, where if you make 0, if you don't move at all, that's 0. If you make 1 step, that's 1. So another metaphor can blend with this one to give you other things like 0 in this case. So what does this tell us about lambda calculus, or what's the sort of cognitive science that would be behind lambda calculus, or what would the sort of sociologists and philosophers say about lambda calculus? So again, this is, I think, another intriguing Twitter discussion where someone says type theory and lambda calculus are eternal, but libraries, they're ephemeral and they're just no good. So I think that the highlight is this. So lambda calculus, that's really like discovered, but AngularJS, nah. The ideal world of mathematics doesn't have Angular in it. Maybe React is there, I don't know. So what can you say about these claims? Well, the one that I'm really going to sort of relate this to is this really intriguing idea from computer science that links programs and lambda calculus with proofs in mathematics and category theory, called also Curry-Howard Lambic correspondence. And I think that's one argument that people sometimes sort of use or refer to when they want to say, oh, there really is something deep. So the idea here is that a lot of lambda calculus constructs, like types, functions, and tuples, they happen to correspond quite amazingly to proofs in programs. So type is like a formula, and if you can construct a program of a given type, then you prove a formula. Function in programming happens to correspond to implication, and function application is the modus ponens rule from logic. Tuple will sort of happens to correspond to conjunction, and it links with stuff in category theory as well. So the idea here is, well, there really must be something deep about the universe here, because we've just found that the same thing exists in 3 different branches of sort of human knowledge. So is there something deep? Well, the first answer, or the first potential issue, is that you just can't even relate programs and proofs, because it's something that philosophers call category mistakes. Proofs refer to some sort of world of logic, and programs really refer to empirical a posteriori knowledge. So program is this like physical stuff, and proof is mathematical thing, and you can't just sort of take these two together and treat them as the same thing. This sort of criticism was really well, they didn't have Twitter shitstorms in 1988, but it caused something like this, where James Fetzer, a philosopher, wrote this paper, The Very Idea of Verification, where he says program verification is a category mistake. It's literally nonsense, because you can't have proofs about programs. Proofs are a different world than programs. You can observe programs, you can do sort of empirical tests like scientists, but they're not mathematical. So that's one sort of possible thing to say about proofs and programs. I think another sort of maybe more easier to swallow perspective is this idea that it really depends on the sociology behind it. So what Lakatos's proofs and refutations would tell us is that the analogy between the 3 is very carefully sort of evolved fit. And if you look at what you need to link the 3, you just don't take any arbitrary category theory. You take Cartesian closed categories, which is a very particular monster. You just don't take any proofs. You take proofs in certain kinds of intuitionalistic logic, and you take special, or one of the sort of several kinds of lambda calculus. So the fact that the 3 match might very well just be because through the process of proofs and refutations, we've learned how to carefully construct them so that they align. But it's just the sort of sociology, the human work behind it that make them fit. It's not like Curry Howard, who are 2 people, woke up in the morning and they're like, haha, boom, now I have this perfect eternal knowledge dropped on my paper, it matches. It's really the sort of human process behind it that made it work. And one more part of the human process behind it, I think, is the sort of cultural background, where even in science, it very often happens that somehow, magically, one idea gets sort of independently invented or discovered around the same time. And I think this very often happens because there's just a community of fairly well-connected scientists who sort of talk to each other, work on similar problems, perceive similar things as important, and use the same methods for investigating these. So I think these three really, you could see them as the sort of the mathematician's network solving the same problem with logic and lambda calculus. That's sort of going back to Hilbert again. And it sort of all happened in this enterprise of searching for foundations of mathematics and trying to formalize this sort of human logic inference so that it can be done mechanically, which back then meant you'll hire some cheap labor to do the symbol pushing. But the three ideas really sort of come from the same sort of soup of ideas. So that's one way of explaining why they happen to be so similar, and you can fit them together. And the cognitive scientists, they would tell you, well, they're probably the same because they're all derived from the same embodied experience using some conceptual and layering metaphors to sort of understand this or construct this abstract way of thinking about something that we experience in the world. Sadly, they didn't pick lambda calculus as one of their examples in the book. But really, the sort of interesting question would be, how are these ideas constructed from embodied experience? And that's a tough question, and I don't really have a full answer, but I do have a couple of points or a couple of pointers on sort of what they might need, what the aliens might need to understand lambda calculus, or what's the sort of embodied experience that you need to have for something like lambda calculus to exist. So would aliens understand lambda calculus? I'm not using Twitter quotes this time. This is from a Quora question, and I think it was even not talking about lambda calculus, but about LISP specifically. So that would make James Fetzer, the philosopher who's angry about category mistakes, very upset. Would aliens understand lambda calculus? That was the question, and one of the parts of the answer is, well, any intelligent species is bound to come across logic. This is a well-known computer scientist answering without really giving any evidence. So we're sort of, in science, we're all very careful about arguing carefully, except when it's on Quora answers. It just is the case. And once they have logic, they'll run into program-proof duality, and boom, here's LISP. And I think it's very tempting to believe this if you subscribe to the Platonist ideas, or if you really, because the sort of experience you have when you work with logic really is that it sort of has this romance of mathematics. You're working with eternal truth, so surely the aliens would also have some sort of reasoning. So I don't really want to blame anyone for sort of saying this, because if I didn't spend the last few years reading philosophy of science book or philosophy of mathematics books, I would say the same thing, and it's a very natural thing to say. But let's try to look at a couple of things from the sort of cognitive science aspects. And as I said, I don't have a clear answer of like how lambda calculus is sort of constructed, but I think there are a couple of basic constraints that you would need. So one thing, and this is in the Lakoff and Nunez book, where they actually do a bit of work to understand logic, and one of the points they're making is that that sort of build up by a chain of metaphors through things like set theory, from something they call container schema. And this is a this is really sort of physical embodied property of the world, where if I have a little black thingy and I put it in a glass and I put the glass in a jar, then the black thing will be in the jar. So that's something that sort of is a property of sets as well. When I have X is a member of A and A is a subset of B, well, then X will also be in B. And the sort of mathematics here is constructed because this is how we perceive the world. So that's one thing. It's sort of, and when you think about it, you say, well, is there any world where if I put a coin in a glass and then the glass in a jar, the coin will be outside? Well, that takes a bit of creativity, but might be. So what the book has is that this is how you can explain the modus ponens. So given two container schemas, A and B, and some object X, if A is in B and X is in A, then X is also in B, which happens to have very much the same structure as function application. So if I have types A and B and a value X, and a function A to B, and X, then the sort of f of X will be in B. So I haven't done all the sort of cognitive science research that would be necessary to really claim that this is how things like application in lambda calculus can be understood, but I think there's definitely sort of some link with what they call the container schema. So that's one thing you might need. The other interesting thing about lambda calculus, and this is going back to the method that the cognitive linguists use, is to look at the language that we use to talk about things. Because the language is often an indicator of how we think about stuff. So evaluation in lambda calculus is done using beta reduction, and reduction has a lot of sort of language intuition associated with it. So when you reduce, it means to bring down to a smaller extent, or to lower in degree, or to bring down to a lower rank. So you have something that's sort of bigger, and you reduce it to something smaller. And this really has an important sort of property, is that it has some direction. When you're reducing, you go from one place to another, and you can't go back. If you have 2 plus 4 and you reduce it to 6, when you can't really easily go back because you don't know whether 6 was 2 plus 4 or 1 plus 5. So the other, I think, important metaphor that you need for actually even having lambda calculus is this sort of notion of direction or directedness. And I'm going to wrap up by looking at some concrete aliens. So E.T. is very much like humans. He would probably have lambda calculus. But the two other interesting ones is Lam's Solaris and the Arrival movie. How many people have seen The Arrival? How many people don't want to hear any spoilers about The Arrival? I'll try to be careful. But the Arrival movie is really sort of about these aliens that have very strange language. And the language has this sort of circular nature, which in the movie also sort of affects the perception of time, but they don't have any, I think they can't really have any notion of directedness, direction. So given that for reduction you need this directedness, maybe they wouldn't even be able to think that something can be reduced. And they might have a different sort of foundation of reasoning that's based on sort of everything where you can sort of morph between states and reverse everything, but they might really not have any sort of idea for reduction. The other movie is Solaris, or sort of Stanislav Lem's book. And this one is even more curious because the alien life form, or the thing that's in the movie, is this sentient being which sort of seems to be the entire planet. So this kind of alien, there really is only one thing in the world. And would that sort of alien living in a universe where there's only one thing, would it even have numbers 1 and 2? Like 6-month-old planet doesn't look at your Mickey Mouses and says, haha, 1, 2, and 3, because there's nothing like that in that sort of cognitive perception. So that's another sort of creative alien that maybe wouldn't have lambda calculus. And the last one, so I sort of made this up, and then because I wanted some alien that lives in a very chaotic universe, maybe in sort of gaseous planet, then obviously I looked up on Wikipedia. There's a list of aliens by life form. You scroll down to gaseous aliens. There's like 5 of them. So pick one of them. There's interstellar dust cloud. And I think what would be really interesting about sort of aliens that have this sort of very chaotic nature is that if you look at chaos, there's no clear boundaries. There's no like inside and outside because it's just sort of all flowing in the space. So those kinds of aliens, even if they as all the, there's one in Star Trek as well, if you're a Star Trek fan. Those aliens, if they have reasoning, it must be based on something else than on containers with this clear sort of distinction of inside and outside. So that's another potential thought. So would aliens understand lambda calculus? I think I sort of tried to use this question to make a couple of important points. The one is that this is really a question that the people in the humanities building have been thinking about. And Platonism, which is this idea that mathematical entities are universal truth, is really just one of the beliefs. And some people mainly people who don't believe this will say it's just a religious belief, it's a religious claim, because you can't tell. There's no experiment you could use. Like, you could blow up the whole universe and then check if there's still mathematics, but it's kind of hard to do. So you can't test this, and hence it's not really a scientific claim, it's just a religious belief. And philosophy of science and philosophy of mathematics has a lot of interesting thoughts. So there's the sort of social aspects of mathematics where it really, you can explain how things evolve by looking at what people are doing, or the cognitive approach where it's product of embodied mind. And I think in summary, it really depends. Like boring aliens would probably have lambda calculus, but if you try to be a bit more creative, there's a lot of things that you could say where they wouldn't. Thank you. I think I started 5 minutes late, so we might have some time for questions. In the meantime, here's the books you can read.
So, tremendous talk. I wanted to address the question of directionality with the aliens from Arrival, and again, trying to steer clear of spoilers, but like they do clearly have an understanding of physics. They build starships, they travel across the universe. They actually talk about things that will happen, but even putting that aside, you know, at least on the macroscopic scale, observational physics does appear to have a directionality, despite the fact that the equations appear to be symmetrical. So time itself must give them some notion of direction, even if they can perceive things concentrically. So I would posit that such aliens would still have a notion of directionality. They must, in order to interact with sort of the physical universe, even if their mental processes are able to abstract beyond that.
Yeah, so I think this is, I think it's really, really hard to sort of look at these concrete ideas like the sort of arrival or even my chaotic things, because whenever I start to think about it, I really get into the same problem where they really must have some inside, outside, or some directionality. And I sort of think, well, when you watch the movie, you sort of see it as the human projection of what the aliens do. So we see them as sort of behaving as if there was directionality, but maybe there's a way in which they can do all these things they do without having directionality. And I don't want to sort of, the sort of Christian idea of God who's timeless is another problem. Like, God wouldn't have Lambda Calculus if he's timeless, but.
With that, thank you very much. We don't have time. I'm sure we can grab Tomas later. Cheers.